All right, in today's lecture, we're going to go over pressure. Um, so we're going to introduce the concept of pressure from a continuum viewpoint. So we're going to consider a small area, A, through which we have a fluid at rest. On the sides, the area exerts a compressive force, F normal. But an equal and oppositely directed force by the area on the other side. And if the fluid is at rest, we have no other forces acting on it. So if I have my area A and it's at rest, I have normal forces equal and opposite on my sides. So our pressure, which if we remember is force divided by area, is going to be the limit as our area goes to an infinitesimally small area of our normal force divided by our area. So what are the units of pressure? The SI units of pressure are the Pascal, which is denoted by PA, and 1 Pascal is equal to 1 Newton per meter squared. In English units, it's the pound force per foot squared. What is the actual units, but what's more commonly used is the pound force per inch squared, which is referred to as PSI. And this one is PSF. And then we also have one standard atmosphere, or ATM, an ATM. So 1 ATM is 1.10325 times 10 to the 5 pascals, which is 1 bar, which is 760 millimeters of mercury, or 29.92 inches of mercury. Absolute pressure is pressure with respect to zero. It's pressure with respect to the zero pressure of a complete vacuum. So I want to note that absolute pressure has to be used in all thermodynamic relationships. Okay, so now that we know what pressure is, how do we measure pressure? One way to measure pressure is by the use of a manometer, which measures pressure based on the height of a column of fluid. Since pressure at equal elevations in a continuum of a liquid that's at rest are equal, so if we look at our our picture here, the pressure at point A and the pressure at point B are going to be equal. If we were to do a force balance, the gas pressure, P, is going to be our atmospheric pressure, because that's what our system is open to at the top, plus our density times gravity times the height of our fluid column. So pressure measurement devices indicate the difference between absolute pressure inside of the system and the absolute pressure outside the measuring device. We have to use absolute pressure in all of our thermodynamic relationships. The magnitude of this pressure difference is called gauge pressure or vacuum pressure, where gauge pressure is when the pressure of the system is higher than our local atmospheric pressure, so P gauge is P absolute minus P ATM. And vacuum pressure is really the opposite. So vacuum pressure is when our local atmospheric pressure is greater than the pressure of the system. So P vacuum is equal to P ATM minus our absolute pressure. So I'm going to draw this out on a little graph. So here's a line of zero pressure. This is my absolute pressure. This is my atmospheric pressure. Then say I have another system where my absolute pressure is this. This height difference is P gauge, whereas this height difference is P vacuum. I'm going to do a quick example of calculating. I'm going to do two quick examples of solving problems using pressure. We have a storage tank holding natural gas. In an adjacent instrument room, we have a U2 mercury manometer that's connected to the storage tank. It has a height of 1 meter. If the atmospheric pressure in the room is 101 kilopascals, and we know the density of mercury and we know gravity, we want to determine the pressure of the natural gas. So what do I know? I know I have a U-tube mercury manometer. I'm trying to find pressure. So what do I have? I have a chamber of natural gas, and it's connected to a U-tube manometer that has some height L, which is 1 meter. And we have P8TM at the top. And there's a point A and a point B, and we know those pressures are the same. So PA is our P gas, and PA is equal to PB, which is equal to P8TM plus rho GL. So P gas is equal to P8TM plus rho GL, which is equal to 101 kilopascals plus 13.59 grams per centimeters cubed, which I'm going to convert my units. 1 kilogram is 10 to the 3 grams, and 100 centimeters cubed is 1 meter cubed, times 9.81 meters per second squared times 1 meter times 1 kilopascal is 10 to the 3 newtons per meter squared. So I get 101 kilopascals plus 133.3 kilopascals is 234.3 kilopascals. That is the pressure of our gas. Oop. The next problem we're going to look at is we have a piston we have a piston cylinder assembly. We know the cross-sectional area of the top of the piston. We're trying to determine the magnitude of the force acting on the shaft. If we know what the gas pressure is, and we know the masses of the shaft and the piston, and we know that this piston is not moving. So if I was to do a force balance in the y direction, I would find out that the weight of my piston plus the weight of my shaft plus the force of my atmospheric pressure plus the force pushing down on the shaft minus the force pushing up by the gas has to equal 0. So if I solve for my unknown force, I know that my force is equal to the force of my gas minus the weight of my piston minus the weight of my shaft minus the force from my atmospheric pressure. Now, F gas is my pressure of my gas times the area of the piston. It's the area of which the pressure is acting. Now, the area of my piston is pi times the diameter of my piston squared over 4, which is pi times 10 centimeters squared over 4, which is 78.54 centimeters squared. So F gas is 3 bar times 10 to the 5 newtons per meter squared per bar times 78.54 centimeters squared times 1 meter squared, so 100 squared centimeters, is 2,356.2 newtons. In a similar manner, FATM is PATM times the area of the piston minus the area of the shaft, because PATM is only acting here, which is 1 bar times 78.54 minus 0.8 centimeters squared times 10 to the 5 newtons per meter squared per 1 bar times 1 meter squared per 100 squared centimeters squared. So FATM is 777.4 newtons. So now the weight of my piston plus the weight of my shaft is going to be equal to the mass of my piston plus the mass of my shaft times gravity, which is 24.5 kilograms plus 0.5 kilograms times 9.81 meters per second squared times 1 newton is 1 kilogram meter per second squared, just to clean up my units. And this is equal to 245.3 newtons. So now the force, which again is the force of my gas, minus the weight of my piston, minus the weight of my shaft, minus my atmospheric pressure force, is going to be 2,356.2 minus 245.3 minus 777.4, which is equal to 1,333.5 newtons. That's it for this lecture. In our next lecture, we're going to go over temperature.